So, welcome, ladies and gentlemen. Can everyone see and hear me? So, question. So, while we wait, just wanted to ask if we will be continuing with the same timetable even after we return to campus. So, yes, the idea with these online sessions is that we have these sessions in the time slot allocated for the subject. So, to introduce myself, my name is Mr. Heistek Grobler. I'm an astronomer, and I will be teaching you this semester. So, question, I cannot hear. How do I fix this? Can everybody else hear me? So refresh your page or check your browser settings. If it's not your browser settings, please also check your computer settings or device settings. So I'm also recording this session, and the recordings will be available after class on YouTube, and also will be available on a Google Drive link. Can everyone see the slides I'm sharing? Okay, so a few questions. Let me go through a few of these questions. So what will the assignments take? So I will discuss the assignments in this intro lecture. Additional textbook, there's a few additional textbooks you can use, but I have a prescribed textbook. I'll go through the textbooks as well. So can everyone see my introduction slide? Okay, so just to save a bit of bandwidth, I'm going to turn off my camera so you'll all be able to see me. So in tonight's lecture, we're just going to discuss what the course is going about, who I am as your lecturer, some cool stuff in astronomy, a bit of an introduction lesson, and questions. So one thing for this course is I like to have this course as interactive as possible. So right now, currently, I'm really liking how you engage in the chat. But if you have the confidence for it, and I encourage it, you are more than welcome to unmute yourself and ask a question as well. So here are my details. Like I said, I'm Mr. Heistek Grobler. My office is room 568 in the Department of Physics, Natural Sciences building. I have an open door policy, so if I am on campus, you are more than welcome to pop into my office at any time, and I will help you to the best of my ability. If I'm not on campus, you can reach me via email anytime as well. After this class, I'm going to share a Google Doc link with you. I just want you to add your student number, name, surname, and cell phone number to the Google Doc. Then I will create a WhatsApp group for the class. I found that the WhatsApp group helped last year, especially with this remote learning and online teaching. So for now, while under this lockdown regulations of level 1, all of our classes will happen via Blackboard Collaborate, where all our classes will be recorded and then uploaded to YouTube and Google Drive afterwards. If you connect through the through the UP Connect portal, then the Google Drive link will be zero data rated and you can download the videos. So our prescribed textbooks is Horizons Exploring the Universe, with its authors, publisher, and ISBN 13 number. And here is how the textbook looks like. The bookstores on campus and around campus have stock of the textbook. If you know where to look online, I'm sure you can find a free PDF version of the book, but this is the book we are going to use, and we're going to use the examples in the book as well. So this is a really good book for astronomers. Yes, Mr. Els, I see you have risen your hand. So the edition we're going to use is the, let me just fingers the 14th edition. Then additional textbook, this is not a prescribed textbook, but it's a additional textbook that you can use, is Astronomy. It's an open source textbook. It's compiled by a few observatories and institutes such as NASA, JPL, and a few observatories. It's open source, so you can download the textbook from this link. It has the same work in as prescribed textbook, but I prefer the prescribed textbook. And this is how the textbook looks like. Yes, I will, as soon as I've set up the links, so the link to this textbook. So let me just copy and paste it. Here's a link to this textbook. So I will, in the next 2 weeks, communicate our semester test date, assignment date, and examination date to everyone. I'm just waiting for a few dates to be finalized. And then we come to the next part of how the course will be structured and how marks will be allocated. So we're going to have a semester mark and an exam mark. Your semester mark is calculated with your semester test. That's going to be 50% weighting of your semester mark. Assignment, that's going to be 40% of your semester mark. And a few quizzes, that's going to count 10% of your semester mark. So your quizzes is not going to be every week. It's going to be throughout the course, just to test your knowledge on, to see if you understand and where I need to change my teaching method. Then we're going to have an exam in June, August, and that's going to count 100%. And then both of these are going to have 50-50 weighting to get a final mark of 50%. So there's only going to be one big assignment for this module. Just to give you back a bit of background information on the assignment, you guys are going to observe the moon from wherever you are for a minimum of 10 days, see at which phase the moon is on, and then you're going to write me an article about what you observed. So just a little bit of house rules for this course. So semester dates, assignment dates, and quizzes can be changed to different dates and days, but I need a majority vote of the class to change it. So majority vote rules in this class. And then there's going to be no absence from tests and assignments. If there's going to be no sick days. So if you are seriously sick and miss the semester test or handing date of the assignment, you please give me a doctor's sick note within 3 days of the missed event. And then, very, very, very important, if you miss the deadline of an assignment, I won't accept any late assignments. Then last of all, you need a minimum semester mark of 50% to qualify to get entrance into the exam. Do you all understand what I mean with 50% minimum semester mark? Okay, cool. So, question, is the course difficult? No, the course is not difficult. The course is, it's quite a nice course, I must admit. Um, Back when I was first year, this course didn't exist. So this is a course I wish I had in my first year. This course, you don't need any extreme scientific or math background for this course. Everything we're going to need is we're going to learn it in this course. So before we're going on about this course, let me ask, uh, what are you guys studying? What is your majors? Are you physics student, computer science students, math students, engineering students? Okay, cool. So I see the majority will be physics and computer science with a few other courses in between. That's really cool because this course will give you nice background knowledge of astronomy and perhaps will awaken your appetite for astronomy. So the main object of this course is to provide you a non-technical, so that meaning you don't have to have the necessary background information of physics and math to do astronomy. So in this course, you will be familiarized with different methods, techniques, and theories required to do mathematics. So how long have I been doing astronomy? I've been doing astronomy for the past 10 years now. And question, does a 10-day start today? No, it doesn't start today. I will tell you when it starts as soon as I upload your assignment. So I know where you are sitting. You are sitting there asking, okay, what makes me qualified to teach astronomy? So a bit of background information about myself. So can you continue with astronomy until your third year of computer science? Unfortunately not. If you want to continue on with astronomy, then you need to take the physics majors. But in some circumstances, you can motivate to take additional modules for non-degree purposes. So to give you background about myself, I'm one of the crazy, stupid people that did a BSc and a B.Eng at exactly the same time in my undergrad. So after I did my BSc and my B.Eng, I did a master's in radio astronomy. I'm currently now pursuing a PhD in astronomy. And with this, I have been working. So currently, I'm a researcher at the Hartbeespoort Radio Astronomy Observatory. That is a research facility of the South African Radio Astronomy Facility. So, in short name for the facility I am is called HARTRAO. I'm going to paste it in the chat. And I'm also a researcher and lecturer here at the University of Pretoria at the Faculty of Natural Science, Department of Physics, the Astronomy Group. So with my career, I've also spent some time at SALT, the South African Large Telescope. I have been to spend a lot of time at the Greenbank Observatory. I'll come to the Greenbank Observatory. That's the world's third largest telescope, and it's situated in Greenbank, West Virginia. And I've also spent some time at the University of California, Berkeley in the United States as well. So you can see my field of expertise to astronomy is in one of those gray areas that fall between physics and engineering. So, show you a few cool projects I worked with and a few cool things in astronomy. So back in my undergrad, this is one of my crazy projects. We built a two-man canoe entirely out of concrete, and we raced against different universities. So the quizzes, it may, depending on, it can be weekly and it could be bi-weekly as well, or sometimes every second week or third week. Then another project I did is, so will we have the opportunity to see the stars at an observatory? So it all depends on what's happening with our COVID regulations. Under level 1 and above, visiting observatories is strict due to health and safety. But if the restrictions are less strict, then I perhaps can arrange a field trip to the Hartbeespoort Observatory. So in this project, I built a rocket and satellite that I launched. So I reached an altitude of 1.2 kilometers, then launched a small little satellite in the atmosphere, did experiments, and I brought the satellite back down with parachutes. So here's the image of first stage separation of the rocket. And here's the time I spent at the SALT telescope. Are you guys all familiar with SALT? Okay, so I see here's a few of yes and no answers. So, SALT is the largest optical telescope we have in the country. It's situated in Sutherland. It's constructed out of 90 mirrors, and each mirror is about odd 90 centimeters in diameter. So in total, SALT is about 11 meters in diameter. And in this is the observatory where I am, the Hartbeespoort Radio Astronomy Observatory, or short HARDRAO. So this is a radio telescope. So let me ask, do you guys know what's the difference between an optical telescope and a radio telescope? Okay, so let me say, who of you have heard about an optical and radio telescopes? Okay, so let me give you a explanation of how it works, but before going on to what's the difference between the two, this is also one of the other toys we have at ArtRail, actually one of three toys. It's a satellite laser ranger. So we use these lasers. So if you think about your normal red laser point that you use to shine on your board with or play around at home, it has a power output of oddly 1.3 milliwatts. This laser is 1.3 gigawatts. So have you ever thought about it? How do you keep satellites in orbit? How do you know the location exactly where satellites is? You use one of these lasers. You shoot the laser to the satellite. The laser reflects back. We know what the speed of the laser is. We record the time for the laser to return, and then we can calculate the position of the satellite to an accuracy of 3 millimeters. So question, isn't that a plane hazard? Yes, that is a plane hazard. So we have a radar system that picks up planes and cameras that look to the sky. So if any plane comes in 10 kilometers of our sight, the laser turns off automatically. And yes, there are giant reflector plates left on the moon. So we use these same lasers to track the orbit of the moon. So we have a lunar laser ranger. We know where the location of those reflector plates is on the moon. We wait for photons to reflect back, and then we record a time for the photons to reach us, and then we can calculate the orbit and position of the moon as well. This is a picture of the Green Bank telescope. This is the third largest telescope in the world. It is 50 stories high, 110 meters in diameter. So that means it's bigger than a rugby field. So if I go back a few slides, this is our Artemis Hook telescope. It's 26 meters in diameter. The Green Bank telescope is 110 meters in diameter. So this was also the coldest day of my life. It was minus 27 degrees outside. So here's a nice side view of the telescope as well. So this telescope is in Green Bank, West Virginia, in the United States. So the cold doesn't, only where the cold becomes a problem is if you go below minus 30 degrees, then the oil in the gearboxes to move these telescopes, actually the oil starts to freeze and it becomes a jelly, and then you can't move the telescope. So everything colder than minus 30 degrees, we stop operation. So to give you the perspective, let me go back a few slides. So what precisely is the difference between this radio telescope and this optical telescope? So except the size, so you're starting to touch on an interesting question. So size becomes an aspect, but yes, wavelength also becomes a aspect. Yeah, I'm sure you guys are all familiar with the electromagnetic spectrum. Okay, so we know in electromagnetic spectrum, visible light forms part of the electromagnetic spectrum, right? So yes, different types of readings. So if you imagine the electromagnetic spectrum as the keys on a piano, visible light can be represented by one of the black keys on the piano, where the rest of the electromagnetic spectrum are all the other keys on all the other keys on the piano, and that represents the rest of the electromagnetic spectrum. So if you have an optical telescope, then you can only look at visible light, and some telescopes can also observe the near infrared. So with the radio telescope, you can see more. So with a radio telescope, we are not interested in visible light, but we are interested in the rest of the spectrum. We want to see radio waves, gamma rays, X-rays, and all other radiation coming from an object in space. Does that make sense? Okay, cool. So we use telescopes for what we want to observe and what is designed to observe. So optical telescopes is for visual images, radio telescopes for less of the electromagnetic spectrum, but we can construct an optical image from a radio telescope because we know what wavelengths correspond to which colors. So we can construct a nice image. So, something cool. Can you guys guess what this is? Yes, it's a microwave in a 3 centimeter thick steel box. So why do you think we put a microwave in a steel box? Yes, radiation. Of course, if you use a radio telescope, it picks up electromagnetic radiation from everything. So, in a normal optical telescope, to put a light source next to it is a big no-no. So, you don't want light to interfere with optical telescopes. So, optical telescopes is built far away from civilization and cities to keep the light pollution as low as possible. But with a radio telescope, you have the exact same problem. With a radio telescope, you're not allowed to have any sources of electromagnetic radiation close to the telescope. So to show how sensitive the Green Bank telescope is, if you would theoretically put a cell phone on Mars, it will completely blind the Green Bank telescope. So yes, light pollution for optical, and you can call it radio pollution for radio telescopes. So for example, the Green Bank telescope is situated in a radio exclusion zone. It's a 90-mile radius where there's no Bluetooth, no Wi-Fi, no radio, no microwaves, no television, no overhead power lines, no overhead telephone lines, to keep interference down as possible. Okay, so can repeat the question. What's the difference between optical and radio telescope? So the big difference is, so questions, so taking your phone, phones are not allowed at the observatory. So how do you prevent cell phone radiation at the location? Everyone has to put their phones on flight mode. We continuously scan for emitting radiation, such as Wi-Fi hotspots, Bluetooth, and that person gets fined. And we make sure there's no cell phone towers close enough that can give you a signal. And someone's mic is open. Does someone want to ask a question? Okay, so just to recap, what's the difference between a radio telescope and an optical telescope? So let me go back a few more slides. So here's the optical telescope again. So optical telescope looks at visible light. So you've all heard of the electromagnetic spectrum that you can visualize as the keys on a piano. So an optical telescope looks at visible wavelengths, and that represents a black key on a piano, where the rest of the electromagnetic spectrum represents all the other keys on the piano. So an optical telescope only looks at visible light, where a radio telescope looks at the rest of the electromagnetic spectrum. So you look at radio waves, gamma rays, infrared, X-rays, near infrared, far infrared, and all other wavelengths that form part of frequencies that form part of the electromagnetic spectrum. So, questions. So what would happen if someone got hurt or something? We have landline communication, so we have fiber lines that run into the observatory and surrounding areas. And we plug phones and all our devices, such as computers, networks, into optical fiber networks, and that keeps the radiation to a minimum at the observatory. So what would happen if a phone was on Mars? So if there would be a cell phone on Mars, you would theoretically blind the Green Bank and all other radio telescopes on Earth. So why does the Hubble telescope use optical instead of radio waves? Hubble was designed for a specific purpose. So we want optical telescopes in space as well, and to get the best optical pictures where there's no light pollution is outside the Earth's atmosphere, and that's why Hubble was constructed. Yes, so flight mode helps with radiation because your cell phone has a transmitter, a cell phone signal, Bluetooth, Wi-Fi, and that causes havoc. I'll come to a picture later showing why. But one other thing with telescopes, that is with optical and radio, more radio, your electronics causes interference on a telescope itself. So all the electronics on a radio telescope, more exactly the receivers, so The optical telescope has lenses to focus the incoming light, and at so in a radio telescope you don't have lenses, but you have a receiver, and the receiver is cooled down to minus 12 Kelvin to keep electronic noise out. So minus 12 Kelvin is oddly minus 260 degrees Celsius. So what is the radio interference at RKBS look like? We have very little interference because we are down in a valley, so sometimes cell phone signals peek through, but interference is not too bad. So we cryogenically cool our receivers to minus 12 degrees Kelvin. That's cool. So we went on a field trip there. So unfortunately, due to COVID, field trips are not allowed, but as soon as that's lifted, then I'll see if I can arrange a field trip to Hardrail. Then this is also at Greenbank. What do you see interesting about this sign? Why is it so? You can't drive petrol vehicles close to the telescope because the telescope picks up your spark plug, where diesel vehicles doesn't have spark plugs. And you're also not allowed with the Greenbank telescope to have a camera within 1 kilometer of the telescope, especially a camera in a digital camera, because the telescope picks up the shutter of your camera as well. So everywhere at our observatories, we will have these RFI reminders to guess. So RFI, radio frequency interference. So everything that causes RFI is not allowed on site. So on the image left is one of the data centers of the Greenbank Observatory. So in this image on the left, that is 680 terabytes of solid state drives. And how long do you think it takes to fill up those drives? So that's 680 terabytes. It takes 12 hours to fill up those terabytes. So the Greenbank telescope does about 680 terabytes in 12 hours. So in Hardrau, we do about 6 terabytes in 12 hours. And then the image on the right is called a spectrometer. So a spectrometer is used to look at emission and absorption spectrums of elements and objects being observed. So that's just raw data. So from the raw data, we construct images. And yes, all the data is kept. So the observatory has its own data center, and then it's backed up from external data center somewhere else. So this is just the raw data coming from the telescope, and this is transferred to a cluster in the data center, and then it's archived. So who interprets all the data? So the majority of the raw data is sent to processing machines of specifically built software to sift through the data a bit, and then the data will be passed to astronomers to manipulate and go through and see if they can find anything. So what is data? Data is everything we can record of these telescopes. So for optical telescopes, that will be images. Radio telescopes will be images as well, but also what frequency are we detecting? What is the power or amplitude of that frequency? What is the wavelength? And then we go through all that data to interpret what we are seeing and do research on it. So on average, how large would one image be? So that's a good question. It depends on what you want to do. We don't really talk about the image. We talk about a data set. So it depends on what is being observed, but a typical size for a normal data set is usually around about 40 gigs. And then what format is the data recorded? So it's recorded in FITS format. So in astronomy, we like, I'm going to type it in the chat, we like a format called .fits, but I see there's a new movement that goes to HDF5, but right now it's .fits. So that's why computer science is also important for astronomy, because we are now running into the big data problem. Are you guys familiar with big data? Okay, so a few yeses and a few no's. So what big data is, it means is we are now in this age receiving a lot and lots and lots and lots of data that requires lots of space, lots of processing to sift through it. So we need new methods and ways to store these data and to comb through these data to look for information. So that's where computer scientists come in, because we need new ways to store data, archive data, go through data. So this is the University of California, Berkeley, an awesome place also. I've spent a lot of time here. It's situated in San Francisco in the US. And one of the research groups I'm involved with is the CASPER Research Group, the Collaboration for Astronomy Signal Processing and Electronics Research. So I'm just going to type the acronym for you guys. So if you have free time, it's also cool to go through the CASPER website. I'm going to post you a link as well that you can go through. So there's a lot of research articles on the page and information. So this is one of the projects I'm involved with. So this is the Casper framework with a roach. It stands for Reconfigurable Open Source Architecture Computing Hardware. So it's a processor. So you're all familiar with normal computer CPUs and computer GPUs. But this is a third type of processor called an FPGA, Field Programmable Gate Array, that falls between a CPU and a GPU. You can use CPUs and GPUs for astronomy purposes and general science and engineering, but the only problem with CPUs and GPUs are they are already specialized into doing a specific task. So if you want a CPU or GPU to do something completely different, it takes a bit of a workaround to get them reprogrammed to do whatever you want them to do, where FPGA is completely open source, not specialized, and extremely well at parallel computing. So I use these FPGAs to construct a spectrometer to do spectroscopy on objects in space. So this is an image of one of my spectrometers that I developed. So this is a object we are going to discuss in this course. It's a maser. So if you type it in the chat, spectroscopy if you want to Google it. So a maser stands for microwave amplification by simulation of emitted radiation. Is almost the exact same acronym as laser. Laser is laser amplification by stimulation of emitted radiation. So instead of a beam of lasers and photons, we look at a beam of microwaves. And in space, there are these molecular clouds. And if a particle moves through these molecular clouds, its electrons jump to a higher valence orbit, and that radiates microwaves, and we can detect these microwaves. So here we can see a little filter with a little peak. So on the x-axis, that's our channel, and channel can be correlated into frequency. And on our y-axis, we have amplitude. So if you see that little blob, on the little blob, there's a little right corner peeking out. So if we zoom in on that in a narrowband mode, this spike we are seeing is the emitted microwave radiation coming from that molecular methanol cloud at 6.6 gigs. So we know this is methanol because methanol emits radiation at 6.6 gigs. So that is what spectroscopy does. In spectroscopy, we know certain elements emit certain radiation at certain frequencies, and certain elements absorb radiation at certain frequencies. So this is something cool I wanted to show you of what I do for a living. So now we come to a bit of our introduction part for tonight's lecture. So what is astronomy? Astronomy is the study of the universe, the celestial objects that make up the universe, and the processes that govern the life cycle of those objects. So this is a picture of the South African Large Telescope, or in short, SALT. So what is now radio astronomy and optical astronomy? So radio astronomy is a subfield of the field of astronomy that is based to find methods and techniques to measure, capture, analyze radio frequency, electromagnetic radiation with the means of radio telescopes. Do you guys recognize this image? That's the Very Large Array in the US. So, if you watch a few of the sci-fi movies, such as Close Encounters of the First Kind, you've probably seen a lot of these sci-fi movies. Please tell me you guys are sci-fi fans. Okay, cool. So a lot of sci-fi fans. So last year I asked the class the question. So I asked the question to the class last year. Have you guys seen the movie The Core? Why no? I got the exact same answer from the class last year. So I'm going to type it in the chat, The Core. Please go watch this movie. You guys have a big gap in your education. If you're sci-fi fans, you need to watch this movie. But I'm also a huge sci-fi fan. I watch everything sci-fi. My favorites is Star Trek, Star Wars, Stargate, SG-1, and the list goes on. So if you're a big sci-fi fan, Stargate, also watch it. So the VLA is an iconic telescope usually used in the sci-fi movies. So this is what I talked about, the electromagnetic spectrum. So here we can see the entire electromagnetic spectrum with gamma rays on the left, longer radio waves on the right. So the higher the frequency, the shorter the wavelength. The lower the frequency, the higher the wavelength. So you can see in this, the visible light or the visual spectrum only forms a little small part of the electromagnetic spectrum. So optical telescopes look at the visible part, and some of them looked at the infrared part, where radio telescopes looks at the majority of the electromagnetic spectrum. I take that as a compliment. Unfortunately, we are not having face-to-face class. If you were in a lecture right now, there's a few short video clips I usually work in between my slides to keep your attention and to show you some cool stuff. But unfortunately, that does not work over Blackboard Collaborate. I've tried it last year, but it sucks that we can't show videos. So, something interesting I want to show you. I will send you guys the links. I can upload it into Google Drive as well, but I will upload the links as well. So, you guys are probably familiar or heard about the SCI project. Okay, so the SKA stands for the Square Kilometer Array. So that's a project to build the biggest telescope on Earth. But design principles, let me go back a few slides, has changed in the last couple of years. So with normal optical telescopes, the main restriction on an optical telescope is how to build your mirror. We have a size constraint on the mirror. The bigger the mirror, the more light we can detect. But if we just construct a bigger mirror, the mirror weighs more, meaning we have to reinforce the structure more, and becomes quite a difficult exercise. So if we go look at radio telescopes, let me go back a couple of slides. So radio telescopes again, such as the Green Bank or Hydro telescopes, the bigger the telescope means the bigger collecting area you have, the better resolution you have. But the problem is the bigger you build it, then the structure becomes a problem as well, because the bigger structure, the heavier it is, the harder it is to move it, and it becomes more difficult. So one way to solve this problem is to do what the VLA is doing. And that's called an array of telescopes. That means you, instead of building one giant ass telescope, you build a lot of smaller telescopes, and if you add their surface area together, you have one giant telescope. So, question, is there a reason why optical telescopes look at a small slice of the EM spectrum? Yes, because with optical telescopes you have a giant mirror and you can only pick up visible wavelengths with it. Because if you go to the EM spectrum, if you have higher such frequencies such as X-rays and gamma rays, that goes straight through the mirror. And if you go to shorter wavelengths, such as radio waves, that can be reflected off the mirrors. So it depends on what you design your telescope to do. Optical telescopes are designed to look at the visible spectrum, and that's what they're extremely well to look at the visible spectrum for. If you look at, for example, radio telescopes, all radio telescopes can't see the entire electromagnetic spectrum. They can see about 70% of the electromagnetic spectrum. It depends on what your telescope is designed to do. So your radio telescopes is usually designed from long radio waves all the way up to UV, or the other way from UV all the way up to X-rays, because the location of the telescope is an important factor of what you can see. The position, the height, the atmospheric conditions, that's all principles we're going to discuss and talk about during this course. And I see here like Arecibo. So yes, Arecibo was the world's largest telescope. So yes, there are 8 X-ray telescopes around the world. So before South Africa got the bid to build the SCI project, and to prove of concept that we can build a giant array of telescopes, there was a concept built called the CAT telescope, Karoo Array Telescope. So the prototype was built at Hartbeespoort or Hartrouw, and then moved to the Karoo in Carnarvon and Northern Cape, where 7 of these was constructed, called the CAT-7 telescope. And as I said, it stands for the Karoo Array Telescope. And that showed the world that we in South Africa has the know-how of how to build telescopes and operate telescopes. And then we got the bid to build the SCI telescope. So from this design, so in the middle you can see these struts going up that holds the receiver, but that struts block a little bit of the surface area of the telescope. It moved over to this design. It's called a Gregorian offset with one arm that holds the receivers. So it blocks less of the surface area of the telescope. And 64 of these has been built in the Karoo in Carnarvon, and that's called the meerkat telescope. So not meerkat as the animal, it's actually a nice wordplay. It's meer, so in Afrikaans for more telescope. So more of cat, nog van kat. So that's why it's called the meerkat telescope. And the meerkat telescope will become the SCI telescope. So SCI stands for Square Kilometer Array. So the world's largest telescope is FAST telescope in China. It's 500 meters in diameter. Then we had Arecibo that unfortunately collapsed. That was due to damage from tropical storms, and that was 305 meters in diameter. But FAST and Arecibo cannot be moved in any way. They are built in a valley, and they make use of the Earth's orbit to look at different objects. Then we have the world's third largest telescope, the Green Bank telescope. That's 110 meters in diameter. That's also the world's largest steerable telescope. It can move up and down 90 degrees, swing around 360 degrees. And then the construction of the SCI, that will be the size of 1 square kilometer. So this is test data of the meerkat telescope. So question, do you have to teach to become an astronomer, or are there jobs that just allow you to do research? Yes, there are jobs that allow you to do research, and there are jobs that you have to teach as well. So for example, in South Africa, there are 2 governing bodies for astronomy. The one is the SAAO, so the South African Astronomical Observatory. They govern all optical telescopes in the country. All our optical telescopes are now moved to Sutherland. There are a few still in Bloemfontein. There's one that's not being used in observatory in the city. There's a few in Cape Town at in observatory that's not been used, but everything is moved to Sutherland. And then we have SARAO, the South African Radio Astronomy Observatory, that governs all radio telescopes in the country. So that is Hartrouw, CAT-7, meerkat, and SCI. So if you are an observatory such as SALT or Hartrouw or meerkat, Then you have certain positions where, for astronomers, we just do research. But if you are at a university, usually at a university, research positions are not that much. So there are still peer research positions where just do research, but majority people at university has one semester where they teach and one semester where they do research. If that answers your question. Pleasure. So 50% of my time I'm either 50% of my time I'm at Hartbeespoort and the other 50% of my time I'm at UP. So in this image, the left top corner, we can see the first image of Cat 7 in 2012. And all those red images we can see are different galaxies. Then we have Meerkat 4 in 20. So Cat 7 is all 7 of the Cat telescopes. Meerkat in 2016 top right, that's 4 of the Meerkat dishes. Then we have 2016 on the left and 2017 on the right. So you look at a 2017 image, you see a bright dot in the center with these two flares popping out. That is the supermassive black hole in the center of our own galaxy. And the rest of the dots in the background are all other galaxies we can see in the background. So far away, we are speaking of billions of light years. What part you want me to repeat?
So can you please, so I didn't hear the part. Did you say that in the picture of 2017, the bright spot in the middle, that's the black hole in our galaxy, and the ones in the light, like the dots surrounding those, are those other galaxies?
Yes. Oh, thank you for unmuting your mic. I really appreciate it. So in the 2017 picture, the dot in the center with those two flares popping out, that's the black hole in our own galaxy. So this is an image of the center of our own galaxy. So those flares popping out is something we call Hawking radiation, and we'll also learn about in this course. And all the other dots around it are galaxies in the background that we can see electromagnetic waves coming from those galaxies, and we can detect it. So how does image work? The more brighter the image, the higher intensity of electromagnetic waves we can see. And then we get to this image. This is an image of the full 64 dishes in the Meerkat telescope. So going in 2017 from 16 dishes to 36 is a lot more detail popping out. So how long until the black hole completely evaporates? I'm not sure about the numbers, but that will be billions and billions of years. Do you guys recognize this logo? Have you guys heard about the Event Horizon Telescope? So the Event Horizon Telescope was used to take an image of the first black hole. So how the Event Horizon Telescope works is, and how other radio telescopes work as well, is called a principle called Very Long Baseline Interferometry, or VLBI. But we have telescopes around the world. They look at the exact same object at the exact same time, and where you can see these lines on the globe, that is called baseline. So we can construct a virtual telescope that is as big as those baselines. So all these telescopes we can see on this map are all X-ray telescopes, and we need X-rays to detect a black hole. So all these telescopes together is called the Event Horizon Telescope, because we can't directly see the black hole, but we can see the event horizon around the black hole. Are you guys familiar with event horizon? Okay, cool. So something interesting that came out of astronomy that's actually quite funny. So this actually came out of the Event Horizon Telescope development. So they wanted software and algorithms to detect certain things. So to test the first batch of the software, they wanted to find a jam of jar on the internet and looked at the images that returned. And then they wanted a chocolate chip muffin and look at the images that was returned. So to answer your question, so the black holes can't be seen. Unfortunately, they cannot be seen with other telescopes. Currently, we can only detect them in X-rays. And the event horizon around a telescope is the point of no return. So if you think about what keeps our galaxy together is the supermassive black hole in our galaxy, and everything orbits the black hole, and the black hole keeps everything in place. But the event horizon is an imaginary line around the black hole. If you cross that line, then there's a point of no return. Then you will be sucked in. You don't have enough power to escape the gravitational pull of the black hole. Yes, that is quite true. So, yesterday was Spy Day, if you all remember. And unfortunately, Stephen Hawking also passed away on Pi Day. So back in the 60s and 70s, black holes was only theorized, and it was theorized that it might look something like this. And Stephen Hawking was the person that did most of the work we know today on black holes. So with the Event Horizon Telescope, they created lots and lots and lots of simulation to see what the black hole might look like. So this is one of the simulated data that we might be able to see around the telescope, around the black hole. And then when we looked at the black hole, this is what we actually saw. So going back one slide, the simulation and the actual image are very close to one another. That's an important part of science. So what we are actually seeing around this image is the event horizon. So these are, it's called an excretion disk. So that is accelerating X-rays around the event horizon that we can see with our X-ray telescopes. So some other interesting phenomena we're going to discuss in this course are pulsars. Are you guys familiar with pulsars? So we're going to look at different classifications of stars. So when a star reaches the end of its life cycle, certain things can happen to that star. It can go supernova, it can become a neutron star, it can become a black hole. And one of the interesting objects that is left over when a star dies out is a pulsar. And a pulsar is a fast-spinning neutron star. The star radiates a bit of energy on two of its sides, and when it spins around, it's like a lighthouse spinning around, and we can pick up those beams of electromagnetic radiation going across Earth. What do you mean, what I know about VSORs? No, I don't know VSORs, the YouTube channel. But I will definitely go look at VSORs. Thank you for the recommendation. So another interesting object we're going to discuss is quasars. And quasars usually form in the middle of galaxies called active galactic nuclei. But it's also something interesting we are going to discuss. We're going to look at masers that I showed you a little bit about. Microwave by stimulated emission of radiation, almost the same acronym as laser, only where microwave is now substituted with laser. And in this is how a eclipse will look like through a radio telescope. So this was imaged by the Green Bank 20-meter telescope. The Green Bank Observatory has 14 telescopes. So this is by the 20-meter telescopes at 9 gigahertz. So we can see the electromagnetic radiation hitting the moon also gets reflected back from the moon's surface as well. And that, ladies and gentlemen, is our introductory lesson and a bit of information about the course. One thing I would like to add about the admin of the course, every now and then I'm going to take an attendance register to see who attends these classes. I know with online teaching it has become quite difficult, but say at the end of the semester you require 1 or 2% to pass the module or need 1 extra, then I will look how your participation was during the semester. If you have a high participation, then no problem for me to help you out. But if your participation is low, then I might reconsider. Is that fair to you guys? Awesome. So if you have more questions, I will be online for a few more minutes. If you have no more questions, then you're more than welcome to log off. I will, in the next hour or so, upload the Google Doc link for you guys to fill in so I can start a WhatsApp group. We can also have a Discord group. Thanks for that. Then I know everyone don't use WhatsApp. We're going to have a Discord group and a WhatsApp group. I will also share a link for another Google Doc. So the Google Doc will be sort of a living document that you can maintain amongst yourselves. So if you have questions, you can post it in the Google Doc as well. And then I'm here to help you. So if you have questions, you can bug me. I will try to the best of my ability to help you. So tomorrow we can actually start with our first lecture. Then we have, there's going to be no practicals, no tutorials for this class. There's only going to be theory with a few quizzes in between. So when do you need our textbook by? It usually helps to have your textbook as soon as possible, but I know sometimes it can be difficult to get a textbook due to circumstances and availability. So if you know where to find the textbook online, I know there's a few websites and torrent sites that have it. I'm not saying not to do it and also not saying to do it, but if you know where to look, you can find it. So yes, the assignment, you're going to observe the moon from the same place each day at the same time, but I will tell you when to start with that assignment. So where can we practice past papers? So I only took over this course last year, so this is the second year I'm teaching this course. So unfortunately, I also don't have past papers for this course. The previous lecturer that retired took everything with him, so I only have the material that I have created for this course. So unfortunately, I don't have past papers yet, but so how beginner friendly is this class? This class is completely beginner friendly. We're going to start from scratch, and at the end of the semester, this usually will start your appetite and sprinkle an interest in astronomy. So Arecibo collapsed in November last year. So during the course of last year, Arecibo got hit by two tropical storms. And due to the tropical storms hitting the telescope so close to one another, there wasn't enough time to do, they were still doing damage assessment and it collapsed. I'm glad you enjoyed the first intro lecture. So how much recommended time do we need to spend studying this course? So my lecture slides is pretty thorough. So if you just pay attention in the lectures, you will be fine. Um, it's a lot of theory, but you will be fine. So I have a question. What is the difference between cosmology, astronomy, and astrophysics? So astronomy looks at the space entirely, but in astronomy there are different subfields. So cosmology looks at astronomy at a giant scale. So in cosmology, cosmologists are not interested in planets, comets, asteroids, different stars, different solar systems. They are interested in galaxies, how galaxies form, how the universe is expanding. So they look at things on a larger scale. One of my colleagues usually makes a joke and says, cosmology is like the gynecologists of astronomy. And then astrophysics look at the physics in space. So astrophysics is also a subpart of astronomy. So on a scale of 1 to 10, how difficult is this course? I would say the difficulty of this course is a 5 or a 6. So do we need to prepare for the lectures? Do you recommend that? So it helps if you read through to prepare a little bit for the lectures, but I know you guys are first year, you have a lot of modules, so you don't have the time for it. So if you just pay attention in the class, you guys will do fine. But if you want to do a little reading on your own, you guys are more than welcome. So off-topic questions, Star Wars prequels or sequels. I enjoy all of them equally amount, but my favorite Star Wars movie is Episode 3, Revenge of the Sith. So question, are lightsabers needed for the course? Lightsabers are not needed for this course. So how do computer science and astronomy correlate? So yes, computer science correlate to astronomy a lot, because if you look at astronomy, one of the big problems now is big data that we're trying to solve. We need computer scientists for it. We usually need better software to interpret the data, so we need a computer scientist for that as well. We usually need new and better devices to look at the objects with, so computer science help with that as well. So are we going to go through the entire Rises textbook? Yes, we are going through the entire textbook. So how heavily will the additional textbooks be used? So I won't be using the additional textbooks. I will only be using your Horizons textbook. But sometimes, if you don't understand a topic, it sometimes helps to read through a different source just to have a different perspective on it or different definition on it. So question, is there a demand for astrophysicists at national labs? So with the SCI project, the demand will become much larger because the SCI is currently being built. So the SCI will become operational in 2030 is the last timeline I've seen. So right now is a good time to get into astronomy in South Africa. So have you worked on HES in Namibia? Unfortunately, I haven't worked on HES, but I have a few colleagues that work on HES. So I'm going to stop recording now.